seen the effects of watching that basketball game. But it's very, anyway, I'm going to start. We implemented the final adjustments to the midterm exam grading. If you want to know what the adjustments were, you should have received that in your email. It's in the announcements section on Sakai also, and also in the resources. There was one question. There was a typo, and well, anyway, the result was that the right answer was the one that everyone got, rather than the one that nobody got, and that was fixed. And there were a few discounts to half. One of the questions I gave credit for two answers of the three, having to do with the use of AA transpose, either that it was used for compression or that it was used for efficiency were accepted. There was another question that I did give full credit for, but I did so with not complete comfort, because I think the question was difficult but fair. But anyway, here was the story. Basically, you had to think about the Fourier transform of the comb of A times the comb sub A in the frequency domain. And it's, of course, comb sub 1 over A. And so it's a spike at each integer multiple of 1 over A. But it's said in the image, representation, some such. The point is in the frequency domain, the image is periodic with period minus a half A, half of 1 over A, to plus a half 1 over A. You never use the higher frequencies. And so when the question said for the complete image, you should have restricted your answer to that range, the Nyquist, from minus the Nyquist frequency to plus the Nyquist frequency. And in that case, in that interval, there's only one spike, and it's an ordinary impulse of energy 1. And so the answer is that the right answer, the answer I wished you'd have gotten, is that it was the same no matter what A is. Some of you didn't think about the image range and thought, well, there are A times as many spikes from minus infinity to infinity, so it's not the same. But the point is, you don't use all those spikes. You only use the ones in the Nyquist range. Clear? Nevertheless, I decided to give credit for both true and false for that answer. In any case, I think we're done with the exam. Treat it as, among other things, a learning experience, and I'm happy to have you come talk to me about any problems you have in the grading of that one exam. The next thing I wanted to talk about was something in assignment 7. Somebody has pointed out, I'm sure those of you who've gotten started, that there's an edge effect problem. And I consciously want you to design a solution, not that there's a prescribed solution. So let me talk about that. And assume we're at the left edge of the image. The same thing happens on the top or the bottom or the right side. And the data is at the big circles, right? The control values are at the big circles. From the ones at the big circles, you compute the values at the blue dots at the first level of successive subdivision, right? And that's no problem. value of this dot is determined by the surrounding values, and they're available. But from that, you then need a value to its left and a value to its right to compute the red x's at the next level of subdivision, right? And the value to its left isn't available. It's because you weren't able to compute it using the normal interpolation at that point, which would require things to the left and things to the right, right? So you need some reasonable value to put here, so that when you compute linear combinations of this and this and this and this, you have values here. And that's what you have to figure out what reasonable values are. Same thing goes, I mean, you have a value here, and you weren't able to do a general subdivision at that position. All the rest of these, the values here have been modified at each level of subdivision. This one isn't. Right? Understand what I'm saying? Well, one possibility is you decide to just use the original value when that's going to be used in calculating, for example, an x that's at this, something that is, when you're putting in points around here, you need a value here, you need the value added, value above it, below it, right of it, and left of it. And you could say, I use the original value, or you could say, I have some other way, like a weighted sum of this one, and this one, to give you a new value there. But anyway, the point is, you need to think about what reasonable values are, especially in context of the real problem. And the real problem was a rotation. You're doing rotations about some place over here, far from the edge. And the amount of rotation, the delta x and the delta y, the offset of those, is going to be very large because of the large distance, right? And so putting in a 0 is as some value, as if you had a 0, that would be the value out here that was 0. Doesn't make any sense at all, right? So some people said, why can't I just use zeros out there? No. Something more reasonable than zeros. Okay?
Is there an agreed upon, like, the people who made the Gimbal Walk algorithm, do they decide on the boundary thing, or is that
Well, okay, so first of all, the short answer is that's a subject in itself beyond the scope of this course. But to answer your question, there is a subject called apodization without feet. That has to do with what you do when you don't have the data you need at the edge of an image. And among the short answer is there are a bunch of possibilities. There's no single, but one possibility is you make some sort of a fit to the data near the edge, and then you extend that fit. You extrapolate from that fit. It's essentially an extrapolation problem. And which particular fitting method you use, of course, is something to be chosen. You could use least squares, for example. But anyway, there's lots of possibilities, but that's the other possibility is you Essentially, you put data, you only use data inside the range that you can trust it. Questions? Well, I hope people who aren't here get the message. Any other questions? Okay, the topic of this lecture is geometric transformations. So geometric transformations are transformations on position, on x. Till now, we've been talking about transformations on I, right? We've been talking about, for example, linear shift invariant operations on the image intensities. This is not transformations on I, it's transformations on x, and then use those transformations to transfer values at one position to the transformed position. Right? So if a particular x moves from here to here, then what you want to do, if you have an intensity value here, you're now at this x has moved to x prime. You're going to put I at the new place that it moved to. Clear? The difficulty is the answer needs to be in x prime. And so in the x prime coordinates, we want equally spaced pixels, right? And so the x primes need to be at pixel centers, which means that the x's are not necessarily, normally not at pixel centers, which means once you figure out what x mapped onto this x prime, then you need to interpolate the value at that x to get the value that's transferred into x prime. Okay? So there is a class of transformations called affine that, so I want to point out that normally we're talking about x is in the same number of dimensions as x prime, and for this lecture we're talking about 3D. So x has 3 coordinates, x prime has 3 coordinates, and a linear, so a matrix multiplication that goes from R3, from 3 dimensions to 3 dimensions, is a 3 by 3 matrix. And so capital A is a 3 by 3 matrix, and B is a 3 vector with a total of 12 variables, right? 9 for the matrix, 3 more for the B. The B is a translation factor. X is multiplied by A and then translated by B. And A, hey, we studied that. A is a rotation, a non-uniform scaling in orthogonal directions, and another rotation, right? And just to remind ourselves, got to get it out. Let me get it out. Here we go. I got a coordinate system here, a so-called frame, right? And so what we're talking about is a rotation of the coordinate system from here to here, then a scaling in each of the 3 modified coordinate directions. Stretch in here, maybe a compression here, some other stretch maybe in that direction, and then a different rotation, maybe a different rotation. If A is symmetric, then R1 equals R2, but if A isn't symmetric, R1 may not be equal to R2, right? So, what does it take to specify a rotation geometrically? Well, what I want you to learn is that rotations are most easily understood as an axis and a rotation about that axis by some angle. So an axis is a direction, right? And if you think about a direction is determined by a unit vector, and if you think about an ordinary sphere, a particular direction unit maps onto the unit sphere at some particular place on the unit sphere. You know where the unit sphere is, you know where on the unit sphere you are, you know what the direction is, right? And how many values does it take to say where you are on a sphere? How do you tell where Chapel Hill is on the Earth? Longitude and latitude, 2 values. It takes 2 values to determine a direction. Latitude and longitude, for example. And one more to tell the rotation angle about that axis. So R1 takes 3 numbers, R2 takes 3 numbers, that's 6. The lambda thing is a diagonal matrix. It takes 3 numbers, and therefore there are 9 numbers in A, either understood as the 9 values in the matrix A, or as 3 for the rotation, 3 for the non-uniform scaling, and 3 for the other rotation, right? And then the translation by B is 3 more. 12 parameter transformation for affine transformations. If it turns out that your A is a pure rotation, then you have and it's a rotation about an axis through the origin, then you have just 3 parameters, right? If you have what's called a rigid transformation, which is a rotation and translation, then you have 6 values. If you want to add uniform scaling, which is together rotation, translation, and uniform scaling is called a similarity transformation, that takes 7 parameters to specify. And those are called rigid. Rigid transformation, 6 parameters. Similarity, 7. Okay? We are also going to be interested in mapping from 3D to 2D, right? So now we have a camera or your eye looking out in space, and you have a bunch of points out here in 3D. Right? I can only draw it in 2D right now. But the point is that you have a screen somewhere, and you're mapping from points onto positions on the screen. The screen is 2-dimensional, and it's orthogonal to some axis that goes out from the center of the camera, if you will, the focal direction. And then this point, or this point, or this point, or even this point maps onto the same point in 2D. That's indicated by the square, right? And likewise, this point, or this point, or this point, or this point, or this point all map onto that square. the point, of course, is that places that are farther away, places that are farther away in depth get the effective size out here gets mapped into a particular size and is scrunched by a greater factor the deeper the points are. Okay, that's called perspective transformations. And we're going to study something called homogeneous coordinates that turn perspective transformations into affine transformations. Okay, and they will be an expansion of the 3 dimensions into a four-dimensional entity, and then the matrix multiplication will be on those 4-dimensional representations. The final thing we need to study beyond affine is non-uniform, so-called distortion. So if I have a bunch of points in my result image, X, and so these X's are in the X prime space in the result, and this X came from here and was displaced to here, and this place, the value here, came from here, was displaced to there. If all these vectors are not characterizable by an affine transformation, you have what's called distortion, right? So you have essentially a different vector for every pixel to tell you where the intensity came from. So in this example here, it came from rather far away to this value, whereas here it came from nearer. Okay, so sort of the space is being locally stretched or locally compressed, and also distorted locally and rotated locally. And so we will need to think about how to deal with this situation of geometric distortion. So this is an overview for this material. We're going to be first focusing on affine transformations, and especially on rotation, because that's very common, and there's some real nice mechanism, namely Quaternions. We've seen that you can do rotations by matrix multiplication. We'll see what's wrong with that. Computationally wrong, not mathematically wrong. And that there's a better way to do it computationally via something called Quaternions. Okay? Questions? Yeah.
When do you often see geometric distortions? When do you see geometric distortions? Is it usually like in medical imaging?
Certainly see it in you see it in all sorts of imaging. Most people, the lenses in their eyes are not doing a purely uniform transformation. We get distortion itself, and those distortions are dealt with by eyeglasses that try to correct that distortion. I guess that's astigmatism. In medical imaging, very common distortion comes in MRI. In magnetic resonance imaging, the behavior of the imaging depends on what the distribution of the receiver. In MRI, you basically you're using magnetism to generate what are, in fact, radio waves. And the radio waves are received by an antenna, and the antenna is somewhere. And so if you have a coil, a receiver, up over here, you're going to get different distortion depending on the fact that the antenna is here than you would get if the antenna was over there. And they want to use these localized antenna because if you have some brain tumor, you know which part of the brain, for example, you want to be sensitive to. And so MR is a very considerable area of distortion. You look at ultrasound as an example. Also, ultrasound is basically a stimulating, you're sending in high frequency mechanical waves, sound if you will, but above the frequencies that you hear. Okay, and sound echoes, and you're taking advantage of those echoes, but it also refracts and diffracts. And those are distortions that depend on what it is it's echoing, not only what it's echoing off, but what the material is between the place it's echoing off as the echo comes back. Well, the sound wave goes through tissue, bounces off as an echo, and comes back. And in the process, it's attenuated and refracted and diffracted. And that's variable depending on what the actual distribution of tissue types is. So, yes, distortion in lots of situations. Okay. So let's get on with it. By the way, if I cough a little, it's not COVID. I guess I have a little bit of runny nose from the pollen, and then coughing is response to the phlegm that was produced. In any case, for translation, a position X has added to it a vector delta X, and that gives you a X prime, the translated position, right? It's simply specified by 3 values. But frequently, what we want is we have a frame, and we want to ask, what would be the coordinates in this new frame? Okay, so if this guy is at minus delta x and is translated by delta x, where does it end up? At 0, right? And so the point is that the new positions are got by application of the new coordinates are got by replacing x by x prime equals x minus delta x. That is to say, the inverse of the translation that the coordinate system underwent. Right? So if the coordinate system undergoes translation by delta x, the new coordinates are got by x prime equals t inverse of x, which is to say x minus delta x. Right? And this is a general principle that we're going to see. The same thing is going to be for rotation. If you have a coordinate system here, and you want to know what it would be, what the new coordinates would be for rotation, we say we're going to rotate about an axis by theta, right? Some axis by theta. And if you want to know what the new coordinates are, you have to apply the inverse rotation to the original coordinates. If you rotate about a particular axis by theta, what's the inverse rotation?
Minus theta.
Yeah, same axis minus theta, right? That's the inverse of a rotation. Okay, so this is both about, this slide is supposed to be both about what happens specifically by translation, but also this general principle of x prime equals t inverse. If you're not moving the points, but you're moving the values of the points to become positions, values in a new coordinate system. If the coordinate system is rotated. Okay? Okay, so let's talk about rotation now. Rotation matrices we've seen are made of 3 orthogonal columns, each of unit size, right? They tell you if you have the 3 axes, 1, 2, 3, they tell you this axis rotates into some coordinate, this axis rotates into some coordinate, and this axis rotates into some direction, I should say. And the 3 unit vectors in the rotation matrix are simply the image under rotation of the first vector, the second vector, and the third vector in their respective columns. Rotations don't change distances. They don't change angles. And so unit vectors go into unit vectors. And a transformation that doesn't have any stretch effect is measured by its determinant, which is the overall volume change. Okay, so if you have a unit sphere in X, and you map it by a rotation, then you're going to map it onto sort of the same sphere, but with the equator modified, if you will, or the axis of the Earth modified. Both actually, but anyway, the point is that you're mapping something that has the volume of a unit sphere into something with the same volume. And determinant is simply the ratio of volume change by a transformation. That's all determinant is. When you say determinant is equal to 3, you say determinant of A is equal to 3. That means that volumes of size 1 map onto volumes of size 3 in space. Okay? Think everything inside a unit sphere goes into a sphere of volume 3 rather than a sphere of volume 1. Okay? In mathematics, they teach that determinant is about expansion by minors and all sorts of stuff like that. It's perfectly nice algebra, but geometrically it's way simpler. It's simply the volume ratio. All the points inside a space of some volume now map into a space of some other volume, and the ratio expansion factor of volume is what determinants are. I had a mathematics colleague, unfortunately long since passed away, with whom I was collaborating, and I complained to him. I said, Robbie, why don't you teach them that determinants are just volume ratio change? And he looked at me and said, you want us to tell them the secret? Well, now you've got the secret, right? In any case, a rotation doesn't change volume, right? A particular sphere maps onto a sphere of the same size, right? Therefore, these matrices with orthonormal columns, these rotation matrices, have determinant 1. If they're truly a rotation. There are matrices that flip one of the coordinates. You have right-handed rule, and where the first cross the second gives you the third, and the second cross the third gives you the first, and so on, by a sort of screw rule, where you have if this rotates like so, if this is the first, well, let's say, then the screw would move that way, and you have right-handed rule. That's basically what's going on. And if you have a determinant of -1, it's not only a rotation, but one or three of the axes are reflected, right? So this guy, essentially a right-handed rule thing into a left-handed rule thing is what -1 means. It's a rotation plus a reflection. But we're only going to be talking about rotations now. So the determinant is +1. Now, there are a couple of ways of thinking about the rotation. One is as a 3x3 matrix with these 3 orthogonal columns of unit size. But another way computationally people do is they say, start off with your x-axis and do some rotation about that axis. Okay, so like so, all right? Here's my x-axis. I'm going to do a x-axis rotation. Notice that the y-axis and the z-axis now become a y prime and a z prime. And now I have a new coordinate system, x, y prime, z prime. And now I'm going to rotate about y prime, right? Not y, but y prime by some angle. And then you will have modified x and z, so you have an x double prime and a z double prime. And now I'm going to rotate around on the z double prime axis. So 3 successive rotations. And those are called an axis together with the angle of rotation respectively are called the Euler method, Euler angles of rotation. And that's very common. You need to learn about it because some people use it. And it's a bad thing to do. And I'll explain why in a minute. Okay? The third way, and the way I'm going to tell you is much more effective way to think about it and apply, is to think about this idea that you're rotating about an axis that you want to specify by a vector and an angle of rotation. So we have basically 3 ways of applying rotations. One is by one of these rotation matrices that has you specify the 3 orthogonal columns. The second one is by 3 Euler angles, which are applied about the original x-axis, and then on the y prime axis, and then on the z double prime axis. Or we have an axis and angle of rotation, and they're all equivalent. They're all equivalent in the result, but not. It's a different program that you write for each of them. So the point is that for any axis and angle of rotation, there exists a matrix. And it's just useful to think about what the matrix, if you do it with the matrix, what the axis is and what the angle of rotation is, and vice versa. If you have an axis and angle, what's the corresponding matrix? And then there is this thing called Quaternions, which also represent an axis and an angle of rotation. They in fact have one further aspect that they include in what they do, which is a uniform scaling. But in any case, so-called unit quaternions are pure rotations, right? So, and they explicitly show you the axis and the angle of rotation. And so you can go from a quaternion to a matrix, or from a quaternion to Euler angles, etc., right? And vice versa. And we're going to talk about quaternions. Okay, so here's a problem. So a rotation about the x-axis is given by this matrix. It keeps the x-axis mapped into itself. 1, 0, 0 maps into 1, 0, 0. And it rotates the y and the z according to this 2 by 2 submatrix. Where theta x is the angle of rotation about x. So the same story for rotation about y, but this is, be careful, this y is not the original y, but it's the about the y prime axis. And then following on with z, so this is the Euler setup. And the problem is, as given here, something called Gimbal Walk, which says basically if the middle angle is 0 or pi, you don't have full freedom on x rotations and z rotations, which is to say there exist rotations that you can't get to easily once you're stuck with this particular situation. So that's one reason why it's not so good. If frequently we have a situation where we have a rotation in one system and we want to apply that rotation successively. Instead of rotating by theta around the axis, we may want to rotate by 1 degree at a time, up till theta, right? And so this is sort of an interpolation of rotations. Right? And if that interpolation happens to run through this nasty situation, it's going to fail if you try to do it in this computation. So, main story is, while Euler angles are frequently used, and if you're reading people and they say they're using Euler angles, you're going to have to understand what it is. You shouldn't implement them yourself. And they're hard to think about because the different rotations are about respectively different axes. Wow, how do you keep track of it? Okay, I'm going to now teach you something from the mathematical literature so that you can understand what people mean when they talk about these a set of geometric transformations. A rotation of a frame is characterized by 3 angles, right? One way is to think of it as latitude and longitude of the axis, and the third angle. Those are both angles. And the third is the angle of rotation about that axis. But another way of understanding it is if I want to go from here to there, what I'm going to need to do is to, first of all, rotate this guy into the new axis. And that's specifying a direction, and a direction takes two numbers. And then what I have left to do is this, right? Once I've fixed where this mapped onto. And that's one direction. Anyway, three angles. Two specifying a point on a sphere, latitude and longitude. One specifying the final rotation about that. It turns out that if you do the geometry, you will find that a rotation then corresponds to a point on a three-sphere. Not a sphere in the spheres I've been talking about here and that you show in the picture there, the Earth, for example, is a two-sphere. It lives in three space, but its surface is two-dimensional. When we walk on the Earth, we only get a choice of walking in this direction or in that direction or in that two dimensions worth of directions that we can walk at any point on the sphere, right? It's a two-dimensional surface embedded in three dimensions. Well, our unit sphere in two dimensions has the equation, points on the sphere have the property that x squared plus y squared equals 1. And if I now look at a three-dimensional thing, so this guy gets the name S2, and this guy gets the name S3. You can think of it as a sphere embedded in 4 dimensions. And the places on the sphere have the constraint that x squared plus y squared plus z squared equals 1. That's so-called S3. Okay, and it turns out that a particular rotation corresponds to a particular point on that sphere, just like a single direction maps onto S2, the unit 2 sphere. Rotations map onto S3. And they map isomorphically onto it so that all the geometry of the sphere, the 3-sphere, is carried into the corresponding mathematics of the transformation. So the upshot is we have this transformation, which I'll call R for rotation. This is not the R with the double lines of the real numbers. And we have a map, I'll call it M of R, which is a point on S3. Okay, so there's a one-to-one map. Be a little bit careful of points to S3, but since the axis doesn't have any particular direction, I mean, it has a direction but no sense, so-called. That is to say, the axis this way and the axis that way are the same axis. There are actually 2 points on the sphere. And so actually it's a hemisphere here. And that hemisphere gets the name SO3, the special orthogonal group of dimension 3. Okay, there's a bunch of names that you'll see in the mathematics papers. Anyway, this map from the transformation to the sphere is called the exponential transformation. And the map the other way around, from the point on the sphere back to this, is called the log. Mathematicians are so used to this idea that they don't capitalize exp log. But you'd learned exp as little exp, and you meant e to the e to the x, right? And yeah, that happens to be right for the map from R1 to R1. That's to say, from one space to one space, from y equals e to the x. But this is a generalization of that idea. You're mapping the set of transformations, and they use I use capital EXP to make sure you remember that this is the generalization of the little exp, although in the literature you'll see little exp without capitalization. Likewise with log, which is the inverse of exp. Moreover, the transformation is applied at a point. And so these exp and logs get applied at a point. The story is, if you look at the tangent plane at a point on the sphere, you see the tangent plane there. We're talking about a map from a linear space, namely the tangent plane, onto the sphere when you're talking about exp. And you're talking about the map from the points on the sphere back onto the tangent plane when you're talking about log. And it matters where the tangent plane is placed. And so this subscript indicates the place on the hemisphere in this example that that the tangent is applied. Anyway, we're going to see that if we have rotation matrices, we can represent them by the set of entries in the array, and we can talk about the exp of the matrix is the place on the sphere, or the log of the place on the sphere is a matrix. Okay, so this is all so you can understand what people are prattling on about when they talk about exps and logs. Okay. Questions? A very good way to think about rotations is via something called Quaternions. And Quaternions explicitly tell you an axis of rotation, an angle of rotation, and a scaling factor. And they are understood algebraically as something of the form that you see here. A quaternion is a w times 1 plus x times I plus y times j plus z times k. Right? What are I, j, and k? Well, you're used to complex numbers, right? You have a notion that you have a complex number, a plus ib, which you understand as a times the real axis, the real direction, plus b times the imaginary direction. Right? And this is just a generalization of that, except the I, J, and K are each their own kind of imaginary direction. Okay? So, it turns out that the x, y, z tell you the axis direction. And the square root of the sum of the squares of w, x, y, and z tell you the angle of rotation. I'm sorry, the scale factor. Boy, that was a big mistake. The scale factor is the square root of the sum of the squares of w, x, y, and z. And the axis is given by x, y, z. a direction, but not necessarily unit. Okay? And then, why is this so wonderful? Well, because we typically want to compose rotations. Right? We want to first rotate about some axis by some angle, and then after we've done that, we want to rotate by some other axis by some other angle, and so on. And it turns out that these compositions are simply multiplications of the quaternions. And so once you know what the multiplication rules are, you're home free. So I'm going to multiply W1 plus X1I plus Y1J plus Z1K, pre-multiplied by W2 plus X2I plus Y2J plus Z2K, and that multiplication will give me something plus times 1 plus something times I plus something else times J plus something else times K, right? And that will tell you what the composed rotation is, because rotations do compose into rotations. That is to say, if you apply a rotation and another rotation, there exists a single rotation about a single axis. That is the composition of the two. Okay, so in order to get on to quaternions, I'm going to move to a different slide set. It's on your resources file as 6B, and it's slides that were produced by have this here. Let me go. What's this? And it looks like this. Oh. What happened to the projector? So this material was produced by a former dissertation advisee, and it's about rotations. Okay, so how do I change the... So what is a rotation? Well, it turns out that you can specify, if a transformation keeps size and orientation and fixes the origin, then it's a rotation. If it maps the origin onto the origin, if distances don't change, if 2 points before the rotation map into 2 points after the rotation, the distance between them doesn't change. And if you have two vectors and an angle between them and you rotate them, the angle between them doesn't change. If it does that for every set of possible vectors and for every point, pair of points, it is a rotation. I call it the duct test. If it walks like a duck and quacks like a duck, it's a duck. If it satisfies those rules, it is a rotation. So, you know what a linear transformation is, right? If you apply it to alpha x plus beta y, you get alpha times the operation on x plus beta times the rotation on y. So we've seen that these mappings that are rotations correspond to a linear transformation which is implemented by a matrix capital A that has 3 orthogonal unit columns, right? And so if y equals 0, you get f of alpha x is alpha f of x, and if alpha and beta 1, f of x plus y is f of x plus f of y. And we're talking here about linear transformations that are rotations. So rotations have the property that they're a linear map from n space to n space. And in our case, n equals 3, from 3 space to 3 space. Points that a point that is a point in 3 space after everything's been rotated has moved on to a different point on 3 space, right? They have the property that in matrix form, the inverse equals the transpose. This is stuff you've seen before. This is not new, right? R inverse equals R transpose. And the determinant is 1, meaning it doesn't expand or contract space. We also note that the angle, or the inner product, the dot product, which is frequently notated by these angle brackets, the dot product between the rotated x and the rotated y. Okay, so now we have a vector from the origin out to the point x, and that vector rotates from the origin to this rotated x. And likewise for y, we have 2 points in. So this is it turns out that AB is just the size of A times the size of B times the cosine of the angle between them, right? And therefore, the inner product divided by the lengths of the respective pieces is just the cosine of the angle between them. And so the inner product between an x and a y is dot product. And dot product is the first thing transposed times the second thing. Right? So it's Rx transpose times Ry. Right? Rx is a 3 by 1. Rx transpose is therefore 1 by 3. It's a 1 by 3 times the 3 by 1, which is a 1 by 1, which is the dot product. Okay? But the transpose of two things in a linear space is put the things in opposite order and transpose each of them. So it's X transpose Ry. But R transpose R is R inverse R, which is the identity transformation. And so that's equal to X transpose Y, which is the dot product between X and Y. So this says that that if these are unit vectors, X and Y, that the cosine of the angle is not changed by rotation of the space. Right? So rotation, I've just shown you that the rotations leave cosine of angles, that is to say angles, unchanged. And moreover, if X and Y, if theta is 0, that is to say you have an identity rotation, it remains the case that the X and the Y size independent for whether they're rotated or not. I didn't say that right. But anyway, the point is that Rx the inner product of something times itself is its x component squared plus its y component squared plus its z component squared all to the half, right? And according to this rule, Rx comma Rx is equal to XX. And that thing is what we call the square of the distance of X from the origin, or equivalently, the square of the size of the vector X. Okay, so the upshot is rotation matrices do what we said. They satisfy the duct rules. They keep sizes alone. They keep angles alone. They do implement rotation. We know if we want to do successive rotations, we can multiply by the first rotation matrix and the result by the second rotation matrix. And be careful. It matters, the order matters. When doesn't it matter? What is the property about R1 and R2 that would make it so that it didn't matter what the order was? They're the same? Say it louder.
R1 and R2 are the same?
All the...
If R1 and R2 are the same?
Well, it's certainly the same works, but it doesn't have to be something more, a little bit more general than are the same.
They're symmetric.
Think geometry.
They share an axis.
Aha, same axis. That's it, right? If you're rotating about this axis by theta 1, and then you rotate about the same axis about theta 2, you could rotate by theta 2 about that axis and then theta 1. If the axis is the same of the two, you can have different rotations because the thetas can be different. But if the axes are the same, then the rotations commute, and otherwise they don't. Okay? Okay, we've talked about this idea of a frame, which is a coordinate system, orthonormal basis, where you have the right-handed rule, where when you rotate 1 into 2, the screw direction gives you the third, and likewise for 2 to 3 into 1, and for 3 and 1 into 2. And if one of those gives you minus the other, it's a left-handed rule. Okay, we've seen this already, that the rotation matrix is 3 columns. The U, the V, and the W axes are the respective images under the rotation of EX 100, EY 010, and EZ 001. All right. This is just a statement of what I already told you earlier in the lecture. If you want to rotate your coordinate system, you have to apply R inverse to the points. You want the new coordinates in the rotated coordinate system. If R is the rotation, then you have to apply R inverse to the points. Okay, so here's the Euler angle stuff I talked to you about. It's complicated and limited. And so we move on to this axis angle way of thinking about things. And so we can think about an axis, which is a unit vector. So we take a vector in that direction and divide it by its magnitude, which is the dot product with itself. It's the square root of the dot product with itself. And we're going to let the size of the vector be the angle of rotation. So you give me a vector. Its direction is going to give you the axis, and its length is going to give you its rotation. And that vector V can be turned into a matrix A sub V, which is simply given by this formula. Right? You have an X component, a Y component, and a Z component of V. And that's the matrix. And it turns out that the rotation matrix is related to AV by this formula. So if theta equals 0, the matrix is the identity matrix, and otherwise it's the identity matrix times the sine of the angle of rotation, which is the magnitude of V, over that value times AV, plus 1 minus cosine of that angle over theta squared times AV times itself. So here's a formula to go from axis angle, as represented by AV, into a rotation matrix. And here's the other way around. If you have a rotation matrix, you turn it into an AV by this formula. Okay? So we now have formulas to go back and forth between axis angle representation and rotation matrices. Right? And now we come to quaternions, and we're going to see that a quaternion is a 4-tuple, W. The quaternion Q is W plus XI plus Y, J plus ZK. and sometimes it's just written as W, X, Y, Z. And the X, Y, Z gives you, is a vector that gives you the axis of rotation. And W squared plus X squared plus Y squared plus Z squared to the half determines the scale factor. Scale factor. Okay. Well, and the last thing you're going to need to know is what the angle of rotation is. And I'm going to stop by pointing to the formula here, which says, there it is. If W squared plus X squared plus Y squared plus Z squared equals 1, it's pure rotation. And the real component is simply cosine of half the rotation angle. Okay? The point is that now we have a quaternion, we can turn it into an axis and an angle, and we can get AB, and from that we can get R, the matrix. Or if we have a matrix, we can figure out what these other components that go back and forth, go from R to AV. From AV, we know the rotation angle theta, and we know the axis, and so we know what V is, and so we know what the quaternion is. So a completely equivalent representation that has some very nice properties when we want to do things like compose rotations. And next time, we'll move on to how you compose rotations and things like interpolate rotations. Remember I said you want to have one rotation and you want to turn it into another rotation, and so on. We'll get to that next time. Okay, so we're done with today's lecture. There are a few people who are listening to this remotely, and I hope the rest of them get to see the recording. Till next time.